Hi, it's Isabella here again, and now we're going to be starting session 6 of our calculations course. And this session is titled Calculations for Institutional Pharmacy. So this is going to be math that you'll see a lot in hospital settings or other institutional environments. The last session we covered calculations for community pharmacy. So you may remember the dispensing fees, difference pricing, or billing for compounds, and we ended with usual and customary. But now we'll get into calculations that you'll see more in the hospital type setting. So this will be dealing with parental dosing, and you may note parental is anything that is outside of the alimentary tract or the GI system. So these routes are primarily dependent on injections. So IV, intravenous, IM, intramuscular, and subcutaneous are those routes. We'll also cover calculations for powdered drug preparation, so medications that come in a powder formulation, and we'll end with percentages. And percentages, what they do is describe the concentration of a particular solution or suspension. So let's get started here. We'll begin with parental dosing. So this is the route of administration for medication that is not dependent upon the alimentary tract. So the alimentary tract is the mouth to the anus. This route is primarily injection. I had mentioned IV, IM, but most are required to be sterile. So that is meaning that they are free from particulates or any microorganisms. So you can imagine if you are getting something through an IV, you definitely want it to be sterile. So for purposes of calculations, we're only going to refer to the IV, IM, and subcutaneous routes because parental involves, other things like the eye drops or nasal inhalation. There's several routes that's not dealing with the alimentary tract, but parental will just talk about IV, IM, and subcutaneous. So these calculations, they do have things that are in common. They're basically all going to be liquids because it's something that you're drawing out to inject or to infuse. So the nice thing is that for all of these problems, you'll be solving for milliliters. This is helpful because you'll always begin your equation with what it is that you're trying to solve for. In this case, it's ml. So ml will be on the top of our first fraction. So now I'm moving to the next slide. We're going to take a look at an example of parental dosing. And in this example, we have an order for digoxin. Digoxin is an old drug. It's used for arrhythmias. So if your heart is not beating correctly, if you have an arrhythmia, you could be on digoxin. And for this one, it's 0.54 milligrams. And the solution that we're using is 250 micrograms per milliliter. So how many milliliters will be needed to fill the order? So remember, we zone in on the unit that we want our answer to be in, which is mLs. So we have mLs on top of our first fraction. What do we know about mLs? Well, you'll always start with the concentration of the solution that you're drawing from. That makes it very helpful because that's the liquid that you're going to be drawing from to get that dose. So this is 1 ml over 250 micrograms. Now remember, the micrograms on the bottom of the first fraction also has to follow to the top of the next fraction to help with purposes of cancellation. So you can automatically write micrograms on the top of your next fraction. Then you ask yourself, well, what do we know about micrograms? You can go back to the problem. We don't see anything more with micrograms. We already used the 250 micrograms, but This is a clue. It should be a red flag. If you don't see the unit that you need, chances are you're going to use a conversion factor to bridge you from one unit to the other. So in this case, it's 1,000 micrograms is equivalent to 1 milligram. So there goes our second fraction in this equation. 1,000 micrograms over 1 milligram. Now again, if milligrams is on the bottom, it's got to be the unit on the next top fraction. In this case, the milligrams is going to refer to the dose that the order is calling for, which is 0.54 milligrams. So notice on this slide the micrograms canceling, the milligrams canceling, and will be left in milliliters. So now you can do this either way, the way that I told you, or if you wanted to go all across, that's fine. But what I usually do is just take 1, then I hit divide on my calculator, and then I punch in 250. Then I hit multiply, and I punch in 1,000. Then I hit divide, the number 1, and then I hit multiply, and then 0.54. And that will give you 2.16 ml. So I had mentioned that some people just like to go all the way across, and that's fine. So in that case, you would just do 1 times 1,000 times 0.54, and then divide by 250 and divide by 1. You'll still get the 2.16 milliliters. So now that we've looked at that on the slide, why don't we look at a video illustration of parental dosing? Now we're taking a look at problems for parental dosing. And these are problems that are taken from chapter 27 in your calculations book. Now, parenteral can mean outside of the enteral system, or more specifically, we think of injection dependent dosing, so subcutaneous, intravenous, intramuscular, intradermal. It's typically what we think of when we see the word parenteral. So in this question, we have a physician ordering 0.4 milligrams of a drug. The label on the vial states that the concentration is 500 mcgs or micrograms per 2 mLs. How many mLs of the drug should be dispensed? Now let's key in on what they're asking here, and they're asking for how many mLs. So remember that we'll start our equation. And what's helpful is that anytime you're doing a parenteral dosing, you are drawing some amount of volume. So you automatically know that you are going to need to calculate for the number of milliliters that you're drawing from that vial. So we will start with the concentration of what's in that vial with mLs on top. In this case, 2 mLs has 500 micrograms of drug present. Now, because we have micrograms on the bottom here, we know that that will be the next unit that we incorporate in our equation. Okay, do we have anything with micrograms? We don't see anything in our problem. Remember, that is a clue. It's a red flag that states, that tells us that we have to incorporate a conversion factor that we've memorized. And because we're going from micrograms to milligrams, we know that 1,000 micrograms is present in 1 milligram. Now, with milligrams being on the bottom here, we know that it'll be the next unit we utilize. And this is where we'll incorporate what the prescriber ordered, that 0.4 milligrams. So we started with this concentration of the vial. this was just a conversion that we've memorized. And this last portion is the dose ordered. So when you punch that out on your calculator, you're going to have the 2 times 1,000 times the 0.4 all over 500 times 1. And what that turns out to be is 800 over 500, and when you divide that out, you get 1.6. And we know that it's in mLs because the micrograms cancel and the milligrams cancel. So our answer is 1.6. Now remember, you're going to always start with the concentration of the vial. You may have to use a conversion factor if you need to bridge between units. And then the last portion that you incorporate is the dose itself. So this is an example for parenteral dosing. Okay, so moving on from parentals, now we're going to venture into powder drug preparations. And I had mentioned earlier, these are drugs that come in a powdered formulation, so it's a powder. And this is due to stability, because some drugs in a powder formulation are necessary because if they are mixed or reconstituted, which means that you add water typically to it, the stability is only good for a certain number of days, and so you don't want that to just go to waste. We want to extend the life on that, so it comes in a powder formulation, and then it's not reconstituted until it's time for the patient to actually receive, administer, or the patient is, going home. Because there are reconstitutables or these powdered formulations in the community setting as well, even though we're introducing it in the institutional side of things. But the directions for the dilution is typically found on the vial or in the package insert. This type of problem or this topics you'll also see in your book in chapter 28 of your calculations book. So on my next slide, I just kind of have some points on powder volume, or the abbreviation PV. This is the volume of space that the powdered drug occupies after it's been reconstituted. It's expressed in milliliters, obviously it's a volume. Some drugs, this powder volume is so big that it has to be considered when you reconstitute, but for others, the powder volume is really not significant. If the entire amount of the drug is to be used, then the powder volume is not as critical because the patient will be using the entire amount. But if there's a partial dose and the powder volume can be substantial, it's important that we get this accurate because we want to make sure that the final volume and the concentration are accurate. So I'm moving on to another slide. Other factors with powder volume include the final volume, or the FV. And the final volume obviously is the volume that you have once everything has been completed. So after you've added the diluent, which the diluent is just, typically it's the water that you're adding to the powder drug. And the final volume is obviously a result from the diluent volume plus the powder volume. It too is expressed in mLs. Lastly, on this slide, we have the concentration. And the concentration is expressed as a weight unit per 1 milliliter. So you see a couple examples, milligrams per ml or units per ml, depending on the drug that you have represented. It's not usually in grams per ml. Typically, you'll see either milligrams or units per ml. So let's move on to the next slide, and you see some formulas here. And the first formula that you see for powder drug calculations is FV equal to PV plus D. And that just means that your final volume is going to be your powder volume added to the diluent volume. Now, if we're trying to find the powder volume, then we'll have to know what the final volume is and subtract the diluent from that. And that'll give us the PV. If we're trying to calculate for the diluent, then obviously we'll need the final volume first, and we'll subtract the powder volume from that. So your question could be any one of these three. One thing that I'll add just to remember is that it is subtraction when you're finding the powder volume or the diluent. Oftentimes I've seen students add the two volumes that they calculate, and it's subtracting. When the question is asking you for powder volume or diluent, it's subtracting. And we'll look at an example here shortly to kind of illustrate that. But the core elements that you see for powder drug calculations is step 1, calculating the final volume. And this is done by starting with the concentration. Because we're calculating for milliliters, milliliters must be on the top of the fraction. Then we multiply by the total drug present. Step 2. Then we take the final volume and we subtract the powder volume to find the diluent. Or you might take the final volume and subtract the diluent to find the powder volume. If we're trying to find the final volume, we just simply add the powder volume to the diluent volume. So let's look at an example for a powder drug problem. We are asked, what is the powder volume of 40 grams of a drug if after adding 89.6 milliliters of sterile water for injection and the concentration obtained is 400 milligrams per ml. So remember, step 1, we have to calculate what the final volume is. And we'll start with the concentration of that final suspension, which they give it to us. And it's 1 milliliter over 400 milligrams. Remember, if you see a unit and no number there, it just means that there's 1 there. So 1 ml over 400 milligrams. Well, if we have milligrams on the bottom of that first fraction, we know that we have to have milligrams on the top of the second fraction. So what do we know about milligrams? You can go back to your problem. I don't see any milligrams. So does that mean we stop? No. Remember, that's a red flag. It's a clue to you that you have to incorporate a conversion factor that you've committed to memory, which will help link or bridge units. So 1,000 milligrams is equivalent to 1 gram. Because we only saw the other unit to be grams, that's a factor that should kind of help influence, oh, okay, I need milligram to gram. So that's the second fraction in our equation. So now that we have grams on the bottom of that second fraction, we know that we have to have grams on that last section. So, and what do we have in grams? It's our total drug there, which is 40 grams. So we multiply all that by 40 grams, and you'll find that your final volume is 100 milliliters. So on the next slide, you see that the last step would be calculating the powder volume. So by knowing that the final volume is 100 mils, we subtract the diluent, which the problem initially gave to us, that it was 89.6. Then that gives us 10.4. So that is our powder volume for this question, 10.4 milliliters. Now why don't we take a look at a similar type question, but with a video illustration. Okay, this is an example where you see an illustration of a powder volume problem. And powder volume is referring to a powdered drug preparation. Because some drugs, they don't stay good or they're not stable for a long period of time once you've added water. So this drug will come to your pharmacy in a powder form, and once it's ordered and ready to go to the patient is when you will add water to it, or what's called reconstitution. So powder volume is referring to the amount of volume that's attributed to the powder in the total volume of the drug order. So you might remember from the slides this formula here, FV, which is the final volume of the product, it's equal to your powder volume, so the volume that's attributed to the powder, plus the diluent. And the diluent is just referring to the water or what you're diluting the powdered formulation with. So final volume equals powder volume plus the diluent. If you are solving for the powder volume, then you know that it's going to be your final volume once you calculate that minus or subtracting that diluent. So it's always going to be a subtraction whether you're finding the powder volume or if you're finding the diluent. So I put these down just to kind of help guide us, to keep us thinking along the right path. So let's take a look at this example here. If we have 95 mLs of sterile water for injection added to a 10-gram bulk powdered drug pharmacy container, the concentration obtained is 100 milligrams per ml. What is the powder volume of the drug? So I like to write this formula out, and then let's jot down what piece we actually are given from the problem. In this case, you can see that 95 mLs of sterile water, that's going to be the diluent, okay? So we're given one piece of this formula, but we don't have anything else. So the first step is we have to calculate that final volume. And because we're solving for a volume, we know that mLs will be on top. You always start with the concentration of what you're making, which in this case, 1 milliliter is going to have 100 milligrams. So keep that in mind too. This is the concentration of what we're making. Now because we have mg's on the bottom, we know that that's going to be the very next unit used. I don't have anything with milligrams though. All I have is this, which I've already used, and then I have this. So if we're going to bridge from milligrams to grams, I'm going to need this conversion of 1,000 milligrams to 1 gram. Now I'm in grams, so this is where I'll incorporate the total drug present, which is 10 grams. So just to backtrack, we're calculating for the final volume, not the powder volume yet, but the final volume. We have the concentration multiplied by, this is just a conversion, and then multiplied by the total drug present. So really that's just 1 times 1,000 times 10 over 100 times 1. So we have, you can count all these zeros and you see that that's just really 10,000 over the 100. And then you can also see these zeros canceling out. And so we have just 100 divided by the 1. So this is the final volume, 100 mils. So we can actually plug this in up here. So now we know two parts of this formula. We know the diluent is 95 mils, and we know the final volume is 100. So then the last step would just be to take the difference. If we know that our final volume is 100 and our diluent is 95, then what's remaining is 5 mils, which is the powder volume. So we had to do a two-step to this, and that is the case with powder volume or finding the diluent. You must first start with calculating the final volume. Then by taking the difference, you will then calculate the powder volume. So this is an example for powdered volume preparations. Please rewind and replay if needed, and run through several more of these practicing problems in your calculations book. It'll be very helpful, and you will find all of those types of problems in chapter 28 of your calculations book. And now we can go on to our next topic, which is percentages. And percentages you'll find in chapter 29 of your calculations book. You probably already know that a percent is just something out of 100. Remember, this is helpful because I had mentioned way back when we first started this that knowing the core definition can be helpful when we get flustered or when we get anxious on a testing day, or maybe we're in the pharmacy and we're trying to figure something out. So just remember the basics. A percent is something out of 100. Now, a percentage strength, that's referring to the weight grams of a drug per 100 mils of a solution. So you see the example here is 80%. And this just means that there's 80 grams of drug present in 100 mils of the drug solution. Now, I typically encourage students to take that number at face value because many times I'll see students that want to move the decimal place over or convert in their head, which is fine. I understand that many students are pretty smart and they can do that, but the problem is when you're being tested or in a real life situation, you might introduce an error because you're not working that out. So I strongly encourage that you take that number for the face value. So that leads me to that second example of the 0.004%. Now take that for face value, meaning that it still means that there's 0.004 grams of drug present in 100 mils of drug solution. Now let's go to the next slide on percentages. So your solution is composed of a solvent and a solute. The solvent is just the substance, and usually it's a liquid, in which the solute is dissolved in. So that's kind of referring to, I like to reference it as the inactive portion, or that 100 mils. So you see the example I have 50%. That percent means 100, and that's referring to the solvent. Now the solute, that's typically the drug. It's the substance that's dissolved by the solvent. So you see again that example of 50%. That 50 is referring to grams of the solute or the drug. It's represented by that number before the percent. So the strengths of many solutions are expressed as a percentage. An example is 0.9% sodium chloride injection, which is the percentage for normal saline. Another example is 5% dextrose, and so forth. So you'll have to know what that means. The problem will not state that there's 0.9 grams per 100 mils. You'll just have to know that. Okay, so let's move on to the next slide. We're still with percentages. Now this is kind of giving more details on what it is that we're seeing. The labels here are giving us more details as to what the solute and solvent is. So you might see a percentage, and then after that percentage sign, you'll see a WV. If you see WV, that means that it's grams of active drug per 100 mils of solution. If you see W/W, you're talking about grams of active drug per 100 grams of drug mixture. If you see V/V, that's referring to milliliters of active drug per 100 mils of drug solution. So remember, typically that solute is referring to the drug, what's being dissolved into the solvent. In any case, that number of your percent, it represents the drug, and the percent represents the solvent in which the drug is dissolved in. Now, you already guessed it. Let's take a look at a percentage question example. So in this question, we're asked, how many grams of a drug are contained in 500 mils of a 15% solution? So since we're solving for grams, you see it in red, we begin our equation with grams in the top of our first fraction. So what do we know about grams? Well, it might appear as though we don't have any information on grams, but interpreting that percent is the key, because you'll know that by definition, that 15% means 15 grams in 100 mils. So there you see our first fraction in our equation. Now, if you have milliliters on the bottom of the first fraction, you know that it has to be on the top of the second fraction. So what do we have that's milliliters in our question that we can use? Okay, you saw it right away, 500 milliliters. So when we take 15 grams divided by 100 milliliters and then multiply it by 500 mils, because that's what the question is asking for, we get 75 grams. You also see the milliliters canceling there, and we're left in grams. So just remember, the key elements for percentages is knowing how to interpret a percent. Typically, it's grams of drug per 100 mils of drug solution. You'll always start with the units that you're solving for, because in some questions, they may not ask you how many grams are found in something. They might ask you how many kilograms or how many micrograms are found in so many milliliters of a solution. But keep all fractions true with conversions that you've memorized or with information that the problem has presented. And lastly, you must know the conversion factors for the more complicated problems. So conversion factors are still an ongoing concept that we have to commit to memory. So why don't we conclude this session with looking at a video illustration of a percentage problem. Okay, this is an example that you're going to see percentage used, and percentages are found in chapter 29 of your calculations book. And this is an example, again, taken straight from your book. In this question, we're asked, Dovanax is a topical ointment available in 0.005% concentration. How many milligrams of the active drug are contained in 60 grams? So let's kind of key in on what they're asking here, and you can see we need to find out how many milligrams. Okay, that is so important because it'll help us start our equation correctly. We're asked how many milligrams of this active drug is found in 60 grams. So I don't really have anything with milligrams here. I see this 60 grams, but don't have anything with milligrams. So this is a key that you're going to use a conversion factor or an equivalency that you've committed to memory. So because we're working with milligrams and grams, we know that we're going to need that type of bridge. 1,000 milligrams is what's found in 1 gram. Because I have gram on the bottom here, I know that that will be the next unit that I incorporate. Do I have anything with grams? I do have this 60 grams here, but you're not going to use this number because that will stop your equation. There's nothing that I know about the 60 gram that I could put underneath here. I need to incorporate this. And it might be wise just to write yourself a little side note. Anytime you see a percent like that, write down what it means. We're talking about a topical ointment here, so this is not a liquid formulation. This is going to be weight here. So this actually means that I have 0.005 grams of active drug in every 100 grams of this particular ointment. So that's going to be helpful in incorporating this into my equation. 0.005 grams of active drug is found in 100 grams of the topical ointment. So I know this is both grams, but remember the top one is referring to the active drug. This bottom number is referring to the total topical ointment. But at any rate, because I have gram here, I'm also going to have gram there. And it's referencing that total ointment. Now I can incorporate the 60 grams because this is asking how many milligrams of the active drug are contained in 60 grams of this ointment. So you can see that we're just going to have, when you punch all this out, it's 1,000 times the 0.005 times the 60 over the 1 times the 100. And you can see that at the top, when you times all these by each other, you'll get 300. And on the bottom, obviously, is just 100. So 300 divided by 100, we get 3. And we know that it's milligrams because you see your grams canceling here. And again, your grams canceling there. So the answer to this problem is 3 milligrams. So this is an example that you see for percentages. And those are found in chapter 29. The only caution I would give you is make sure that you understand the definitional concept of a percentage, that you're able to see this means a little more than just the 0.005%. It means that there's 0.005 grams of active drug for every 100 grams of the topical ointment. So, like I mentioned earlier, you may want to just write a side note and jot that down so that when you're walking through your